So my name is Markus Schulte. As Laurie already indicated, I'm an engineer by training and I'm a building physicist, and I fear I'm going to bore you with a few numbers. And I'm using as a precedence 1271 Avenue of the Americas, which formerly known as the Time Life building. And the Time Life building is probably one of the classic icons of modernist architecture here in the city. It was built by Wallace Harrison of Harrison Abramowitz. General Bronze were the curtain wall contractors. It kind of identifies and exemplifies kind of the beginnings of modern curtain wall construction here in this country. The architect for the project is J. Bergman, is with Paycop Fried. The owner is the Rockefeller Group, Chris Brill Edwards, Jonathan Bursch, and Dan Bauer. And similar to Glenn, in the context of this forum, it's probably important to note that in Midtown, in Manhattan, there's a tradition of responsible property ownership. All these buildings that you see are strategic assets, and at the same time, there's a pride in owning these buildings and maintaining them well. This building has been maintained well. And the central mechanical plant has been updated quite some time ago. And the reason why we got involved, Arup, is to actually look at the facade and look at these exterior risers on the outside of the building. So we, as engineers, we do not only provide here facade engineering services, but mechanical, electrical, plumbing, energy modeling, and sustainability services. And we look at the building as a whole. And if you look at the building as a whole, you actually recognize that you have these exterior air supply risers on the outside of the building, uninsulated. Very limited amounts of vision glazing, only 4'8", and then 7'2" of what is supposed to be an opaque spandrel panel, but it's just single glazing. It's a single sheet of opacified glass. So not this vision glazing is bad and opaque spandrel is good because it's insulated. In this case, this is just an insulated piece of single glazing. And you see this here, as Glenn pointed out, a lot of these buildings unfortunately have very limited floor-to-floor height, in our case 11 feet 10. And the vision glazing, as I mentioned, is 4'8". And the spandrel, the opaque spandrel, is 7 feet 2. The facade, as Bob mentioned, is just hung down from a concrete downstand, not up to code. The downstand in itself creating an impediment for daylight penetration. So this is what the design team is proposing. And you can see that we are draping a new curtain wall, a unitized system, in front of the existing structural frame. We do not take the glazing all the way down to the floor. We make it flush with a new parameter induction unit along the outside end of the building. Insulation, 4 inches of insulation right in front of the concrete encased steel beams. When one proposes this, one has at a point, one has to walk the morass of building permitting in New York City. And this building is a reclad, it's not an overclad, but a lot of these buildings are maxed out on the existing zoning lot. So if we do, from a building physics point of view, the responsible thing, and we try to establish continuity of shrink wrap of vapor barrier and insulation all around our building envelope, we have to push the new facade out. Hence, we create more square footage on the building. The city and the zoning regulations do not lightheartedly allow you right now to increase the square footage for your project. So here you can see the comparison of the existing condition and the new condition. And then what we did is we looked how do we achieve energy code compliance and how do we mitigate the morass of zoning resolutions and regulations to get a permit for this building. And what we did is we looked at the energy performance of the building and we correlated it to the thermal performance of different systems in the building. In the context of the facade and the recladding of the project, the thermal performance of a facade is not only determined by U value, but at the same time by solar heat gain and by air infiltration, by leakage. The zoning resolutions, they focus solely on U factor. If we look into a higher level of detail into this, what you can do is obviously you can calculate the thermal transmittance through the existing condition. And then what you can do is you can compare it with the proposed condition. And you can see here in U value, if I look at the overall assembly U value, the proposed new curtain wall improves the U value by 42%. Although it increases the amount of vision glazing in the project, it still increases, due to high efficiency glass, it increases the solar heat gain performance by 31%. Air infiltration, it improves by 73%. So these are thermal performance improvements, and the interesting question now is obviously how do these thermal performance improvements, how do they relate to energy consumption? And what we did is we built a whole building energy model, and we looked at the three cases in isolation. What energy savings can I achieve if I improve the U factor by 42%, solar heat gain by 31%, and air infiltration by 73%? There's not a linear relationship between thermal performance of the building envelope and energy consumption over a whole life cycle of the building. In the shoulder seasons, the actual temperatures on the exterior actually will help me saving energy, and incorrect design of the facade may actually lead to a higher consumption of energy. So whole building energy model, here's our model. And here are the results. So in case one, our proposed system, which improves the assembly U value by 42%, leads to 10% energy savings in the building. Solar heat gain, vision versus opaque. Although I'm able to improve solar heat gain on the theoretical element, the actual energy savings I can achieve is only 1%. Huge political discussions about distribution of vision and opaque. In our case, when you actually run it over the whole year and over the whole cycle, the energy savings we see by improving the whole solar heat gain is only 1%. Why is that? It's very simple. Midtown Manhattan is very dense, and we benefit from the building towards the south, which is actually much bigger than ours, which is 1251 Avenue of the Americas. Big improvement in leakage, big improvement in energy. So if I add all of these up here, and I wouldn't have done a mistake here, then the proposed improvement of all these three elements lead to 22% of energy savings on this project. all these buildings that Glenn and Bob and I are talking about, they're very large. This building is 2 million square feet. The XYZ buildings south of these buildings, they average around 2.5 million square feet each. So 2,500 residential units at 1,000 square feet. In scale, these projects offer huge opportunities for energy savings. And what I would like to see is that the code regulations in the city actually incentivize owners to upgrade them and not penalize them. Then the energy savings opportunities here are very large. We had the luck with the Rockefeller Group that they made actually the existing utility bills available of the current operation of the building. And if we compare and project future energy savings, we project that we can save 40 to 50% of the current energy consumption in the building. Huge energy savings opportunities for the city, for us as a whole. Thank you.